Hi guys, in last class we just studied an application car on a circular level road. So we got an expression for the maximum velocity the car can take to complete the circular track. So the expression for velocity, we got that v equal to under root of mu square mu times rg. So the maximum velocity of a circular level road will becomes is purely depends upon the coefficient of friction and radius r. What happens if the velocity is greater than the coefficient of friction? Now in this case, if you can see, if car velocity is greater than square root of mu times rg, then the car will be skid out of the road. So to avoid that, without decreasing car speed, to take turn, or sometimes the coefficient of friction is changes depends upon the rain and moisture. So to avoid that skidding because of mu value changes depends upon weather, so we are adopting a technique which is known as banking of a road. So the mu value will change depends upon the weather and moisture. So to avoid skidding from the road, so we are following a technique which is known as banking on the road. So banking of the road means there is a raise on the road level on one side which is outside of the road. So one side will be the raising up and another side will be the raising down. So the system of raising the outer edge of a curved road. The system of raising outer edge of a curved road above its inner edge is called as banking of the curved road. So the angles through which the outer edge of the curved road is raised above the inner edge is known as angle of banking. So see the definition carefully. The system of raising outer edge of a curved road above its inner edge is known as banking of the road. So this is inner edge and this is outer edge. The outer edge is raised than the inner edge. So this system is known as banking of road. Now the angle at which is risen, so this angle is known as angle of banking. So let's see how this angle of banking or banking as a system will be help us to avoid the friction problems. So if the car is turning in a banking road, now the normal reaction force of the car resolves into two components. So now the normal reaction force resolves into two components. One is n cos theta component and n sin theta components. So one of the component is providing the necessary centripetal force. If the curve having a radius r, so the necessary centripetal force we should need that. Without the necessary centripetal force, we cannot complete a safe turn. To derive the further expression, let's consider a car of weight mg which is acting downwards A car of weight mg going along a curved path of radius small r. So here curved radius. Curved radius equal to small r. And it is having a velocity equal to small v, and the angle of banking that is equal to theta. So we know that the angle made by the raison with the horizontal of the lower level of road, which is known as angle of banking. So because of theta, the normal component of the car R, here shown in the red line, is resolved into two components. So the theta component will be contributes R cos theta, and the vertical component it is, and the horizontal component contributes R sin theta. Now apart of that, if you can see the friction at the tire, so this is very important, we need to understand. The friction is also making an angle with respect to theta. Now the friction force is F is making an angle theta. Now if I take the coordinate axis at here, so the coordinate axis at there, if we can draw, so the friction is making an angle theta with the coordinate axis. Now the friction is also resolves into the components. The small angle here you need to notice. So this is the angle made by the friction. Or if I draw separately, so if this is the friction F is making an angle theta, so the corresponding component of friction is also resolved into two components. So along this component it will becomes F cos theta, and the down component is equal to F sin theta. So these components are resolved as like normal components at here. So in this case, the normal components, the normal action force also resolve into the components, and the friction force is also resolving into its corresponding components. Now this component I can write as F sin theta component, and this component equal to F cos theta component. So this is the necessary observation we need to make at here, and this is the advantage also. Now if I write the balancing equations, it means by equating the forces, along the horizontal and vertical directions, we can get, keep it in mind when you are equating the forces. So let us equate the upward forces and the downward forces. Now the upward forces at here are cos theta, which equal to, there is the one and only upward force which acting vertical upward direction, which equal to the downward forces. Here the downward forces equal to mg, plus along with the mg we got one more component of friction force that equal to F sin theta. So this is the one of the balancing equation I got, let it take equation 1. And we know that the centripetal force will act towards inside. So the centripetal force mv square by r should equal to the inward forces. So here the remaining forces are nothing but r sin theta and f cos theta. So mv square by r equal to r sin theta plus f cos theta. So let me equation 2. So I hope you understand these two equations. So here the necessary centripetal force mv square by r equal to one of the component of the normal reaction force that equal to r sin theta and another component of the friction force that equal to f cos theta. Now if you can substitute in the place of f, since friction f equal to mu times r, here mu equal to coefficient of friction. So if I can take this as equation A and substitute equation A in 1, therefore A in 1, and we can write that r cos theta equal to mg plus mu r sin theta. So let us write the expression for mg. Therefore r cos theta minus mu r times sin theta, which equal to mg. So if I call this equation 3, now let us divide. Now let's divide 2 by 3. Now if you can divide 2 by 3, so second equation equal to, that is mv square by r upon mg. The third equation here equal to mg. Or first you can write that mv square by r, which equal to r sin theta plus f cos theta upon the third equation, here it is mg, which equal to r cos theta minus mu r sin theta. Okay, now let us cancel the terms. So here m is common on both sides, and if you can rewrite the above expression, that equal to v square by r g, which equal to r sin theta plus f cos theta upon r cos theta minus mu r sin theta. For the further simplification, divide RHS by r cos theta. Multiply and divide RHS by r cos theta. If you multiply and divide RHS of the above expression with r cos theta, the equation going to change as v square by rg, which equal to a little correction. So it is the divide RHS numerator and denominator. Divide RHS numerator and denominator by r cos theta. So we are just dividing numerator and denominator with r cos theta. So the above expression changes as r sin theta plus f cos theta upon r cos theta and upon r cos theta minus mu r sin theta upon capital R cos theta. So we made a change. So with this R cos theta, we are dividing numerator and denominator of the RHS. So if you can write the remaining expression, that equal to V square by Rg, which is equal to R sin theta upon R cos theta plus F cos theta upon R cos theta. If you can further split, so it becomes R cos theta upon R cos theta minus mu R sin theta upon R cos theta. So the expression has changed like this. So here one small substitution, that is, since f equal to mu times r, so I can substitute this mu times r value at here. So in the place of f, if I can replace with mu times r, so this substitution I should have done in the above expression, but there is no problem. So after substituting that, let us cut the like terms and r gets cancelled, and in this also r gets cancelled along with cos theta gets cancelled, and this entire will gets cancelled, and again r in the numerator and the denominator in the fourth part will also cancels. Now finally I got an expression that equal to V square by Rg, a simple expression equal to this sin theta upon cos theta. This part contributes to tan theta plus here only mu is left upon the total term contributes a value of 1 minus, so in this case we will get the mu times sin theta upon cos theta, we will get tan theta, that equal to mu tan theta. So the entire expression is turns in terms of tan thetas. And if we need to write the expression for velocity v square equal to Rg of mu plus tan theta upon 1 minus mu tan theta. Just I interchange the terms to remember easily. So finally we got that expression for velocity v equal to under root Rg of mu plus tan theta upon 1 minus mu tan theta. You see, the velocity of the car is converted into the radius of the circular turn and coefficient of the friction and angle of banking, and here g is a constant. Suppose take a special case, if there is no friction between the roads and tires. If there is no friction, sometimes it happens because of the rain. Suppose if there is no friction, so if there is no friction, the mu coefficient of friction becomes equal to 0, so that the safe limit of velocity, the safe limit for maximum speed, the safe limit for maximum speed, which equal to, in the above expression if you can substitute mu equal to 0, the expression will be changes as v equal to under root of Rg times tan theta. In the denominator, mu value becomes 0, so this value contributes 1. In the numerator, so the mu value becomes 0, then only tan theta we will get. Otherwise I will do it quickly. So here I can get 0 plus tan theta upon 1 minus 0 times tan theta, which gives 0. So finally if you can write that velocity v equal to under root of rg tan theta. So this is the maximum velocity. So this is the maximum velocity if the coefficient of friction equal to 0. Now the angle of banking theta for minimum between the tires. So what is the minimum angle of banking in this case? So if I can squaring on both sides, so v square equal to rg tan theta. So we get the tan theta expression, tan theta equal to v square upon rg, that implies theta equal to tan inverse v square upon rg. So the same expression we got in the above the two cases also. So the angle of banking theta for minimum for the wear and tear of tires is given by the minimum angle of banking theta equal to tan inverse v square upon rg. So if we want to move with greater velocity, the angle of banking of the road also should be greater, because the velocity is depends upon the theta or the angle of banking at here. So this is the advantage of the angle of banking. And if the road level is increased, so there is no decreasing of the velocity to clear the circular turn. So this is an application of the motion in a circular path.